All right, this is the video recording for Pre-Calculus Unit 3, Lesson 3.4 on graphing polynomial functions. All right, so this might look a little bit familiar from some of the earlier lectures, but we're going to really make sure we hone in on everything and tie it all in here together, okay? So again, graphing polynomial functions, this is truly what calculus is all about, and understanding how those change. All right, so we have to build a really good foundation of understanding what the basics look like before, again, we try to change them. And how do we calculate those changes, and how do we, again, really look at graphs here. All right, so again, the overall objectives here is mostly to be able to describe a general trend, right, or the general behavior of this function, and then be able to identify those critical points using either algebraic skills or graphical approaches. All right, so looking at our study here. Okay, you can use your graphing calculator to graph the following functions. All right, and again, to show you what that might look like here, let me move my graphing calculator in. Again, please note that my graphing calculator is going to look slightly different than yours. All right, so you might see something though, again, so if we're going to plot this first one, so you would literally write it as you see it, 2x to the power of 2 plus, plus 3x minus 1. Right? And if I hit enter, my graph's going to look something like that. Okay? And that's maybe a graph of group 1 here. Now, if we're looking at group 2, all right, if we're looking at group 2 here, we're going to calculate a new graph. So I'll pick maybe the second one down. So I've got x to the power of 3, okay, minus 2x to the power of 2 plus x, right? And my graph's kind of freaking out there, but that's kind of what that graph looks like there, all right? And so, all right, oh, then that would be because I did not bring down. There we go. Okay. So again, being really careful in particular with how you type things in, and also just knowing what doesn't look right. Right. I didn't know what the shape of that graph was going to immediately look like when I first started typing it in. But upon further inspection, I looked at that x cubed function, and I knew it had to look something like what we've been seeing for our x cubed. All right. But here's basically what you're going to notice. You've got group 1, which are things that maybe look like the blue, maybe have a little bit more added on as we get up in higher polynomials. We got an x to the 4th, x to the 6th, and then our group 2 here has our x to the 3rd, x to the 3rd, x to the 5th. All right, and we talked about this. We talked about this here in one of our previous sessions, but the graphs, it says, think about the graphs in which the right and left hand sides have the same behavior, right? They either both went up or both went down. And what was true about the degree of those? Okay, the answer is that they were even. Okay, and I know it's really hard to see. They were even. All right, so again, your x squared, your x to the 4th, that was the degree of the polynomial, and those are the ones that had the same behavior. All right, now if you had one that went up and one that went down, okay, that would be when you had odd number, right? So the degree of the polynomial was odd. That would be your group 2, those 1, 3, 5s. All right. Now, we talked a lot about this here, but if the leading coefficient is positive, right, that means that the right-hand side is going to be increasing or going up, right? It's going to have that positive y value. And if the leading coefficient is negative, it's going to be going downwards. And again, let me highlight something here that I want to keep reiterating with you. Okay, when we're talking about leading coefficient here, that's if we're in standard form. All right, so you've got to have the highest degree monomial written first, and then the lower ones in order. Okay, I don't want you to get confused if something is out of order, right? If this for whatever reason started with x, then minus 2x squared, then plus x to cubed. All right, this is still your leading coefficient, so you'd have to rewrite that in standard form. All right, now looking at this here, okay, we talked a lot about this, but now we're going to try to, again, re-hone in on our skills and make sure that we're using proper terminology here. All right, so if the leading coefficient of a polynomial function is positive, right, that first a value, then the graph will point up on the right-hand side. So in that positive x direction, it's going to go upwards. And then if the leading coefficient is negative, the graph will point downwards. All right, and how we can express them in more calculus-like terms is we can say if a is greater than 0, right? So that means if a is a positive number, all right, then as x goes towards infinity, f of x goes towards infinity. And what this means is infinity is just a positive number. So if you think about our coordinates here, okay, so we have x and we have y. All right, and let me make that a little cleaner there for you. All right, x and then we have y. All right, this is the positive infinity direction of x. It's going on and on and on forever. Okay, so 1,000, 1,000,000, right? Keep going on. Same thing with our y. We have a positive infinity in the y direction. That just means going upwards. All right, and if we talk about negative infinity in the x direction, we're talking about going to the left, going towards more negative values. And same thing with the y direction. If we're talking about negative infinity, we're talking about going downwards. So basically what this is reading as is if a is a positive number, then as x goes towards larger numbers, y is going to go towards larger numbers as well. All right, it's going to go in the positive direction. All right, next one, if a is less than 0, so if you've got a negative value, then as x goes positive, so as we go this way, f of x, which is our output or our y value, is going to go in the negative direction. Okay, so that would mean as we go more this way, we're going to go more downwards. All right, and then furthermore, knowing the left and the right hand sides, okay, is also important, and knowing how those are going to be in relation to each other. So again, if the degree of the function is even, we're talking about x squared to the 4th to the 6th, okay, so on. If it's even, they're gonna have the same end behaviors, right? So if positive x direction goes towards infinity, if it's even, then so will the negative x direction, right? And that's where we have, our parabola shapes or our curvy shapes that both end up going up or both end up going down. All right, but if the degree of the function is odd, right, like a cubic or to the power of third, then they will end up in opposite sides, right? So one will go up and one will go down. And again, it's all dependent on what your a value is, because your a value determines the right hand side of the equation, and then the left hand side of the equation is determined based on that. All right, so again, showing you what I kind of showed you here, but in a cleaner form, okay, as x goes towards infinity, so we're going this direction, f of x or y will also goes towards infinity. All right, and this is saying if x goes towards negative infinity, f of x will go towards negative infinity as well. All right, so again, it's all about the way that you write it, and the more comfortable you can get with this, the easier that you're going to find that calculus is. All right, it's getting comfortable with the notation, understanding what it means, and again, being able to read mathematical terminology. All right, and I've pretty much been doing this throughout, but again, it reads aloud as x approaches infinity, right? And again, I can let you guys read this here. These are just some of the key things that I've been saying over and over again, and I'll continue to say that there. All right. And moving forward here, again, pre-calculus, we're going to talk mostly about this terminology. So again, as x approaches infinity, or as x gets really, really large, then f of x, or the y, the output, will also get large or positive or go towards infinity. All right, but how we would write that in calculus is we would say LIM, which stands for the word limit, right, which is why it's called limit notation, okay? The limit of f of x as x approaches infinity equals infinity. All right, and that's how you would read that one. All right, so it's saying the same thing. This one's saying that as x goes towards infinity, f of x is going towards infinity. All right, it's saying the same thing here. All right, so don't let that trip you up. Okay, moving forward here. All right, we've seen this in a ton of units, but we got to re-highlight here. Okay, a lot of this is about finding intercepts. Okay, so when we're talking about graphing things at always, okay, if you can find the y-intercepts, the x-intercepts, if you've got vertex and you can find those, right, finding those key points is going to be really, really important for you. All right, and again, x-intercept is where it crosses the x-axis, y-intercept is where it crosses the y-axis. So for the x-intercept, you set for the x-intercept you set y equal to 0. For the y-intercept you set x equal to 0. Okay, and then you just solve based on that. All right, so for example here, to find the y-intercept, you set x equal to 0. So we found out the y-intercept is 24 because everything else canceled out. Okay, then we've been dealing a whole ton throughout this entire course on finding the x-intercepts. Okay, so for this one here, since it's x cubed, it might be more beneficial for you to use our rational root theorem, where again, we take all of the factors of our constant, right? So we've got 1 times 24, 2 times 12, 3 and 8, 4 and 6, right? We take plus or minus all of those factors over the factor for our leading coefficient, right? And so that's a 1. So that one kind of makes it easy. It's plus or minus 1, right? And again, that gets simplified if we can, right? We get rid of any duplicates, and then we went through an entire process for how to eliminate some of these, right? So going through and noticing things like how many times does it change signs, right? So here we go from positive to negative. Well, that's one sign change, right? Negative to negative is not a sign change, but negative to positive is another. So that's 2, right? So based on Descartes' rule, we could have potentially 2 positive roots there. We could have 2 positive roots. All right, and then if we don't have 2 positive roots, when we look at this, we actually plug in negative x. So you plug in negative x everywhere, right? And then you do the exact same thing to figure out if you're going to have some negative roots. All right. But once you find one of them, and potentially using the synthetic division rule, right, you find an x-intercept. If it's easy enough from there, if it's a polynomial or a linear that you're more comfortable with, you can then find the rest of the roots, whether they are real or imaginary, okay? And again, you can also use a graph, or we could, again, verify using a graph. So if you're given this equation here, all right, so if I want to pull up my calculator for you. All right, so I want to, okay, so I will type this in. So if you type in your equation, x cubed minus 5x squared minus 2x, oop, how did I do that? There you go, minus 2x plus 24. All right. And right now I have my zoom in, so maybe I'd want to zoom out here if I can. But all right, but for right now this is fine because I'm seeing my x and my y-axis. I'm seeing my origin right there at 0, 0, and I can look and I see, okay, well, I've got 1, 2, 3. I see it crosses the x-axis 3 times. That means I know that it has 3 real roots, right? It has 3 real roots. All right, and since I have an exponent of 3, I've got x cubed, my degree of this polynomial is 3. So that's telling me that I can only have 3 roots, okay? I can only have 3 roots. So since I can see all 3 of them crossing the x-axis here, right, then that's telling me I'm going to have 3 real roots. Okay, I'm going to have 3 real roots. So again, when you follow through, and this is a zoomed up version, okay, you could do that similar thing on your calculator. You could zoom up and then see, okay, well, it crosses there at 2. You can check by typing into your calculator x equals 2 and seeing if your y equals 0. If it does, great, you found a root. And then you can find the rest similarly or through many of the algebraic ways that we've talked about. Okay, so then very similarly here, okay, your y-intercept, again, you'd set x equal to 0 and you'd solve, so you should get negative 12. Your x-intercept, that's where we're going to, again, solve for our roots there, solve for our zeros. Okay, and a couple other last things here. Okay, so reading this is saying as x goes towards infinity. So as we go in the positive x direction, the question is, is this going to go up or down? Right? Is this going to go up or down? And since our value here is a 1, this is going to go up, which means it's going to go in the positive infinity direction. All right? And since our exponent there is 3, which is odd, that means our left-hand side is going to have an opposite of our right-hand side. So this one, as we go towards negative infinity or go to the left, the graph is also going to go down or towards negative infinity. Okay, and looking at our answers here, right? So this is our answers. Again, you might have to solve a little bit more for your x-intercepts, or again, plugging this equation into your graphing calculator, you could be able to look at or trace that graph along the line and figure out your x-intercepts. Okay. So again, considering the following polynomial here, all right, if we look and use our rational root theorem, okay, that's putting our p's over our q's. So we only have 4 potential options because p is 2. So the only thing that can multiply together to get 2 is 1 and 2, right? And it's divided by 1. Okay, so you've got plus or minus 1, plus or minus 2. All right, through synthetic division that we just worked on in the last couple of units, you can find out that x equals 2 as a root. Right, you can find out x equals 2 as a root, then we're getting to our quadratic that we're more and more comfortable with, right? And this is actually ends up being a perfect square, right? A perfect square trinomial. So you're able to easily factor that into x plus 1 and x plus 1, okay? So now when we're able to solve for our zeros, we have positive 2, negative 1, and negative 1 a second time. Okay, and rather than writing this both, right, you say that negative 1 is a root with multiplicity of 2, meaning multiplicity of 2 means there's 2 of them, right, multiplied by 2. You have it 2 times, all right? And what that would look like here is something that we're super familiar with. X minus 2 multiplied by x plus 1 squared, right, meaning the square is telling us we're doing this twice, right? And that gives us our multiplicity, which is a factor of 2. All right. However, when we look at the graph of this function, again, we can see it only passes twice because technically, right, we've got negative 1 2 times. All right. So it only passes through the x-axis at 2 points, and that would be our negative 1 and our positive 2. Okay, so then if we're focusing on different facets of multiplicity, okay, so we've got x squared, and that would be what this looks like. If we looked at our x cubed, you can kind of start to see a different shape in the graph, right? This elongates, this kind of pulls down here, all right? Even further, right? This starts to elongate, this starts to pull down. And what you also should notice is that the end behavior of the left-hand side of the graph is changing depending on if it's an odd or an even function, right? Odd, it has to be opposite. All right, except for, look, we've got that extra x factor there. So this would be 5 and then 6. So this is actually an even. All right, but again, if we were to factor all these out or FOIL all these out, you would find out that these that both go up and up are the even, right? They're the polynomials with the even exponents, and the ones that are up and down or down and up, those would be your odd ones. Okay, and what you should have also noticed is, again, the elongation of this bump over here, and then the elongation of this flatter region along the x equals negative 1 area. Okay, again, it flattens out more and more along that intersection point, right? Because it's got a greater and greater multiplicity there. All right, so then when we're looking at these graphs here, okay, we're looking at these graphs, just identifying some basic functions are going to be really important for you, okay? So to give you the answers to these in case you're unable to click on them, all right, I've got my x plus 1 squared and my x minus 2, all right? For my longer function, my more complicated function, okay, I've got multiple zeros. So you can actually see I've got 1, 2, 3, 4 zeros. So I've got 4 intercepts, okay, and I've got 2 with a multiplicity of 2, which means it's more flatter at those regions. Okay, so if we were to zoom in here, you would see 1, 2, 3, 4 zeros. And again, 2 of those would have flatter regions. All right, then for my next one here, I've only got 2 intercepts for both of these, okay, but you can see I'm got a higher multiplicity with this one and a lower multiplicity with one of my roots here. So my -4 root here is just a straight -4 root, goes all the way through. There's no extra curving. Right? So there's a lot of things that you could be looking for, and I just only highlighted a couple that I in particular look for, but it is truly dependent on what you pick up on in the patterns that you're able to see. Okay, we did mention this a lot earlier, so I want to highlight it here, but we've got this thing called relative extrema. Right, and that's the local and the local minimum and local maximum. Right, those are those bumps in the graph. Right, those turns. And we talked about this already. But if a polynomial function has a degree of n, right, then the number of relative max or mins that you can have, or bumps or turns, can only be equal to n minus 1. So if, for example, if the polynomial is a function of 5, I can only have at most 4 turns in my graph. Now, it is possible to have less than 4 turns or less than that n minus 1, but you got to be careful with how you say it, okay? It's easy, though, to think about it if you can think of it can have up to, but not more than. All right? And if we look at this here, these things, qualifiers, right? Those are the words in front, they're descriptors, right? So you've got relative and you've got the word absolute, and they go with our min and our max to convey what's the highest absolute point on the graph and what's just a local high point, right? So for example, if we look at relative maximum, that's any point that you see kind of as a peak. So I've got a point at A, C, E, G, and I. Okay, that's a relative maximum. All those are little tiny hills or peaks, right? But the absolute maximum, the highest point on this entire graph, is right here at letter I. Okay, same thing with the relative min. I've got a min at B, D, F, G, and J. Oh, sorry, F, H, and J. F, H, and J. All right, and the absolute minimum, the absolute lowest point here is F, right? The absolute lowest point there is F. Okay, and again, remember, extremas are the highest or lowest points in their section of the graph. Okay, and you got to consider x and y coordinates when you're looking at both of these. So right here, we just really looked at identifying the x coordinates. I know we used letters here, but we would be talking about the x coordinates, and then if we were able to see, we would be able to figure out what the y coordinate is and telling us how high or how low something is. Okay, and that's exactly what it says. Since it doesn't have any y coordinates, you can only state the extreme values according to the specific x coordinates. All right, so then moving forward here, to locate all the relative extremes, the extremas, right, the maximum or minimums. Okay, we can clearly see here, looking at this function, we have 2 obvious bumps in the curve here. And if I look at our graph here is x cubed, right? So x cubed can only have n minus 1 turns, right? So if our n is 3 here, it can only have up to 2 turns in the graph. So looking at this, we see a bump there and a bump there. All right, and that tells us this is a relative maximum and this is a relative minimum. All right, but if we look at the ending behavior on both the right and the left hand side, you can see that it goes on and on and on and doesn't look like it's stopping. So what this tells us here is that it doesn't have any absolute extremas, right? We don't have any absolute maximum or absolute minimum for this graph. It's going to keep going on and on and on. All right, and with calculus here that you're going to learn obviously in the next couple of years here, you're going to be able to do a lot more with this information. But for right now, if you can identify the relative max and mins and then tell me that there is no absolute, that is more than enough. Okay. And again, being able to identify the points at which they occur, okay? At the points at which they occur. Now, technically, it is incorrect to give an ordered pair as an answer when asked for a maximum or minimum, okay? It's asking for the highest or the lowest point. It's not asking for a coordinate, because the coordinate is, think about it like a location. All right, so if it asked where does this occur, you would say it occurs at the point 1, -1, 0 and 1, -4. But if it's asking you just for the maximum or minimum, you would say the relative maximum of this function is 0, right? Occurring when x is equal to 1. So it's saying right here, the highest point, or the relative highest point, our relative maximum is 0 when x equals 1. All right, same thing over here. Our relative minimum is equal to -4 when x is equal to 1. Right, again, it's all about phrasing and saying it in the correct terminology. Okay, so then moving forward here, we have these things called inflection points. All right, and this is where the graph changes from going in one direction to the other. All right, and to find these points of inflection, you need to understand this concept of concavity. And I know I've definitely talked to you about this before, but this is talking about how the graph or the curves bend. All right, and we've talked about it up and down. So if it's concave up, it looks like a smile, or again, I say up cup, right? So concave up looks like a little cup there. Concave down looks like it's frowning. So if we watch this video here,
the region of the graph that curves downward is said to be concave down. The region of the graph that curves upward is said to be concave up. The point at which the concavity changes is called an inflection point.
Right? So there you go. Up, shaped like a cup, concave down, shaped like a frown. Okay? And sometimes there might not be an inflection point, right? It might not be an inflection point. So if we have a graph that only has that downward, right, we don't have an inflection point. It is just all concave down. Or other way around, if you have only that U-shaped, right, like a normal parabola, it might not have an inflection point. The entire graph might just be concave up. Right? And so we'll watch this video here, but I'm going to suggest that you watch this definitely on your own as well, because it's a lot to unpack. But basically, this is bringing it all together and figuring out, okay, if this is what I'm starting with, I can find every piece of information I need in order to sketch a graph. Again, sketch means general idea with hitting some highlights, right? Like an x-intercept or a y-intercept or the general shape of the trend. It doesn't mean it's absolutely perfect at every point.
Find the x and y intercepts. To find the y-intercept, substitute x equals 0 into the function and solve for y. The x-intercept is found by factoring the function and finding its zeros.
Okay, again, through multiple means that we've talked about. Plenty of ways of doing that.
Now, move on to the end behavior of the graph. Since the leading coefficient of the graph is positive, and this is a fifth-degree polynomial, the right side points up. We write. Because the function's degree is odd, you know the left side will behave oppositely, pointing down. This can be expressed as, you can now sketch these behaviors on the graph. What happens between the points that you have drawn so far? The trick is to make a table of x-coordinates between the ones you know and evaluate the function at these new values. Then you can graph these points too. You can use your graphing calculator to estimate the locations of the extreme values and the inflection points.
Okay, and again, this is a perfect example of just a sketch, right? So knowing some of those basic things that we've been constantly looking for. And for the sake of time, I don't want to show you how to do this on your graphing calculator again. All right, all you would do is you need to go to that y equals and you would type in this equation, right? And when you hit the graph button, you should generate a graph that looks something like this, right? So even if you skipped out on those middle points, okay, even if you skipped out on the middle points, as long as you check in your graphing calculator and you're able to sketch relative to each other, right? And by relative, I mean that this point middle between them is higher than this point, right? And this point is low or is higher than this point, right? Being able to sketch that, as long as you have the intercepts, the general trend, how many bumps you're supposed to have, it's a good enough complete graph. Okay. So now we're going to go over the study sheet here. We'll go over the study sheet and go over the answers to that guy. All right. So real quickly here, when the graph of a polynomial function, the right and the left sides have the same behavior. The degree of the polynomial is even, right? X squared, x to the fourth. Now, if the left and the right sides are opposite, they have odd degrees. All right. If the leading coefficient is positive, all right, then the right-hand side is going to point upwards. And if the coefficient of the polynomial is negative, it's going to point downwards on the right side. Again, the left side then depends on the behavior of the right side and if it's an odd or an even function. All right. The way that we read this, the function gets very, very large, right? That's what that means. The function gets very, very large. Okay, this expression is read as when f of x approaches infinity. That arrow means approaches. All right, this one means the function gets very, very small. Again, read as when f of x approaches negative infinity. Okay, and then how we write x goes towards infinity, or when x goes towards infinity, f of x goes towards infinity or approaches, you would write that as the limit of f of x as x goes towards infinity equals infinity. All right, now here an x-intercept is a location on the graph where it touches or crosses the x-axis. The y-coordinate of this point is always 0, and the x-coordinate of this point is often called the 0 of the function. All right, the y-intercept is the location on the graph where it touches or crosses the y-axis. Again, the x-coordinate of this is always 0. Listing the x and the y-intercepts, again, being able to look at the graph and evaluate the graph based on there is more than enough most of the time. All right. For this graph here, okay, you would have to look and say, okay, it's to the power of 4, right? And it's got a 1 there. So this is saying the limit of this function as x approaches infinity, or as x goes to the right, this is going to be infinity because this a value is greater than 1. Okay, so that's going to be positive, so it's going to be infinity. And since it's an even function, it's going to have identical left and right side behavior. So again, the limit as x approaches negative infinity or goes to the left is going to equal infinity as well. All right. Now for this function here, graph below, negative 2 is a 0 with a multiplicity of. The answer is 1. Okay, the answer is 1. All right, and you can tell that because it goes right through, right? There's no flattening. But when we look at 3, it's a 0 with a multiplicity of potentially, right? Not always, but potentially, it's a multiplicity of 2. Okay, and the reason we also know that we have to have 3 zeros is because we've got x cubed, so we have to have 3 zeros, whether they're a combination of real or imaginary, we have to have 3 of them. Okay, looking here, okay, if the multiplicity of a 0 of a function is even, the graph of the function touches the axes at that 0. Okay, so if the multiplicity of a polynomial is even, right, so if it's even, this is considered just touching. Now again, be very, very careful. All right, again, I'm trying to highlight it as much as I can. It has to just be touching, and sometimes it's hard to see on these if you don't zoom in that it's just touching, right? Because we could have had this go up and down very, very slightly, so being really, really careful of that. All right, if the multiplicity of a 0 is odd, then the graph passes through. Okay, the graph passes through. So, for example here with number 10, all right, again, zooming in because it's really, really difficult to see, okay? It's really difficult to see. This one is clearly touching, okay? And this one looks as though it's passing through, okay? So this one looks as though it's passing through, assuming we only have 1 there. All right, so this one is going to have a multiplicity that is even. All right, and looking at our options, it's going to be to the power of 2. This one, since it's passing through, is going to be odd, and that would be either, like a 1, 3, or 5. And since we only have the options here of 3, that means that this, whatever x value this is going to have that multiplicity of 3. All right, and since this looks like it's at x equals negative 2, okay, x equals negative 2, that means x plus 2 quantity has got to have that multiplicity of 3. So right here, x plus 2 multiplicity of 3, x plus 2 multiplicity of 3. Perfect. All right, then when we look over here, this is at our 1, 2, I guess they're saying that that's at x equals 3, so we'll count it as close enough, right? So if it's at x equals 3, we've got to have that x minus 3, and this is our one that touches, so it's got to have our multiplicity of 2. So therefore, our answer is right here. It's letter C. Okay, because again, this one passes through, this one touches, and we've got to be able to work backwards from there. All right. If a polynomial has a degree n, then the graph would have at most n minus 1 relative bumps or maximum. Okay, and then informally, these are called bumps or turns. All right. An absolute maximum or minimum are the highest or lowest points for the entire graph, right? The absolute is the entire graph, whereas relative is just that small piece. All right. So given absolute given absolute or relative max or min of the graph, okay, so the min points would be those two and the max points would be there. All right, and again, how you have to say that is the graph has an absolute minima of 0 at x equals -1 and x equals 3, right? We're not giving coordinates. We have to write it as this is what it is at these points, right? So our relative maximum is 16 right there at x equals 1. And again, this is our absolute because there is nothing in the graph that could be lower. All right, and this one is just our relative because if you notice here, our graph continues to go up and up on either the left and the right side. Okay, so then last question here. The graph that is concave up is like a smile, or I say a cup. All right, and then the graph that bends down is like a frown. And the point where this concavity changes is called our inflection point. Okay, it's called our inflection point. All right, and we'll work through a couple problems in the checkup here. And then what you'll have to do for homework is this 3.4. All right, so I want to be respectful of the time and your request to keep these shorter, so I'm not going to walk through as many example problems as I would have liked, okay? But the reason that is because we're putting together all the lessons we've learned throughout, so it should be a lot of review and a lot of combination here. So let's get started, though. All right, so if I look at number 2 here, okay, so it's asking us to state the x and the y intercepts for each function, okay? So first off, we know that our y-intercept, x is going to be 0. So at our y-intercept, we know that x is going to be equal to 0. All right, so very easily I can plug that in. So f of 0 is equal to 0 to the 4th minus 5 times 0 squared plus 4. Right, so f of 0 is equal to 4, so my y-intercept is at the coordinate 0, 4. Okay, it's at the coordinate 0, 4. All right. Now, for my x-intercepts, right, this is where y is going to equal 0. All right, and what we can notice here is that we've got the polynomial x to the 4th power. So we know since it's x to the 4th power, there's going to be 4 zeros, right? Whether they're a combination of real or imaginary, that's going to be up to our solving skills. But we're going to have 4 zeros here. So when we are done, we better have 4 answers. All right, and looking at this here, we can do multiple approaches here. And the one that I'll do is the one that's new to us that we just learned. Okay, so I'm going to take every possible value of our p or our constant. So it's going to be plus or minus 1 over plus or minus 2 plus or minus 4. All right, and then over our a value, plus or minus 1. So really this simplifies down to plus or minus 1, plus or minus 2, plus or minus 4. All right, and those are possible, right? Are possible real values. All right, and then what I can look at here, is that I have a positive value, then a negative value. So that's one sign change. All right, and then I go from negative back to positive. So that's another sign change. All right, so according to our rules, I could have 2 positive zeros. Right, I can have 2 positive zeros from our selection here. I can have 2 possible. All right. And then if I plug in f of negative x, okay, that ends up being x to the fourth, right? Because my negatives are going to cancel, minus 5x squared plus 4. So same thing, right? For this one, it's the same. I'm going to end up having potentially two negative zeros. Two negative zeros. All right. So I know that doesn't help us cancel anything out. And so this is where you can do multiple things. So you can try doing the new process we just learned and looking for a remainder of 0. Okay, you can also plug in values, so plug in possible values, plug into there, and see which ones you get that equals 0. Okay, which ones you get that equals 0. All right, and what we'll end up finding is that x is going to equal -2, +2, -1, and +1. Right? So it's going to give us our 2 positive zeros, our 2 negative zeros, and then we're going to end up having our 4 zeros total. All right. So moving right along here, I have for number 4, I have 3x squared minus 25x. Okay, so again, if I set f of 0 to solve for my y-intercept, I have 0 cubed minus 25 times by 0. So my y-intercept is at the point 0, 0. Okay, so that's where my y-intercept is at. All right. Then for this one, x-intercepts, what I know is I'm going to have 3 of them. Okay, I'm going to have 3 of them. And before I even get any further, I'm looking at this function, and I can actually factor this function into something that's way more easy for us, right? So if I have 0 is equal to that, I can pull out that common denominator, or that common factor of x, and I have x squared minus 25, all right? X squared minus 25. And wouldn't you know it, this is something we've worked a lot on factoring. Okay, so I end up having x minus 5 and x plus 5. All right, so what this tells me here is, again, if I'm doing my 0 product rule, either this is 0, or this is 0. And again, I need 3 zeros, so I'm going to have a 0 at x is equal to 0. Right? Because that guy set to 0 is going to be 0. And then x minus 5 is 0 and x plus 5 is 0. So my other zeros are going to be at 5 and -5. All right, so those are going to be my x-intercepts here. Okay? Moving forward, for 6 through 10, describe the end behavior of each of the functions by writing a limit expression. Okay, so again, that's where we have our limit. As x goes towards something, what is f of x's behavior, right? And again, if I were to draw blanks here, you basically fill in this part there. All right, so if we look at, let's look at number 8 here. Okay, so I notice that I have an even polynomial and a negative coefficient. So regardless of what happens in the middle, all right, I have a negative coefficient, which means that this is going to be going down. And since it is even, it's going to be the same on both sides. It's going to be the same on both sides. Again, there can be a lot of things that go on in here, but when we're just talking about the end behaviors, there's no point in looking at the rest of this. So the answer for this one is the limit of f of x, right, our function there, as x goes towards infinity is going to equal -infinity. And our limit as our function goes towards -infinity is also -infinity. Okay? If we choose to do one more of these guys, all right, let's look at number 9 here. Okay, if we look at number 9, 5x to the 7th. All right, so again, I have a odd. All right, I have an odd, so I'm going to have opposite behavior, one going up and one going down. my coefficient is positive. So this one's going to go up and this guy's going to go down. Again, lots of things can happen here in the middle, but we don't really care about it when we're just talking about our end functions. So our limit as x approaches infinity is going to equal infinity. All right? And now we're going to have an opposite here where when x approaches negative infinity, this is going to equal negative infinity as well, right? They're opposite behaviors between them because we have that odd coefficient there. All right. For the next little group here, 11 through 13, use the graphs to state the zeros for each of the polynomial. Okay, use the graphs. So if I'm looking here, okay, it looks like I've got a 0 there and I've got a 0 there. All right, so I'm going to have a 0 at x equals 0 and a 0 at x equals 2. Okay, now the question then becomes, all right, it's asking us to look at our multiplicity. So the question is does it pass through or does it touch? Right? Does it pass through or does it touch? So our 0 at x equals 0, since it touches, right? Since it touches, this is going to have a multiplicity of an even number. All right, it's going to be even number, and we'll just write the word even there for right now. Okay? Then our 0 at x equals 2 will have an odd multiplicity. All right? And the question then becomes, how do I know how many I have? Right, and that's going to come right here. This is x cubed. So that means I can have a total of 3 zeros. All right, I can have a total of 3 zeros. So if this one has to be even, then the first number we can have, it will have a multiplicity of 2, right? And since that's going to be 2, this one's going to be 1. And when we have 1, there technically is no multiplicity because multiplicity means multiple, right? So in order to say this, we're going to have a 0 at x equals 0 with a multiplicity of 2. And we're going to have a 0 at x equals 2. All right. Moving down here to 13. Okay, 13. I've got my equation, and this is where I told you do not get confused. It's written not in standard form. Okay, so technically our power here is 3, so we can have a total of 3 zeros. So we need 3 zeros there. All right, we need 3 zeros, and I'm going to have a 0 here, a 0 here, and a 0 there. All right, and 1, 2, 3. So those are my 3 zeros. So there can be no multiplicities. So I'm going to have a 0 at x equals 0, at x equals negative 1/2, and at x equals positive 1/2. Right, and I've got no multiplicity because I can only have 3 maximum zeros. All right. Then for this one here, okay, for this one, for 14 through 16, all right, the easiest way of figuring this out would be to plug into your graphing calculator. Okay, plug into your graphing calculator, right? Get a generated graph and then figure out where the low point or where the high point is. Okay? Where the low point and where the high point is. All right? And you're going to have to use your calculator for that one. And I do believe they posted calculator tips for you for how to calculate the local min and local max, right? And I believe under mine it says calculate, or there's a math, calculate min, and then you can also calculate max. It is under your options. So if I look at my graph here, I have to hit my second button. So if I get rid of that math, okay, I have to hit my second, and then I can hit my calculate button, and this is up on trace, okay, on the trace button. And then what I can do is I can scroll down to minimum, or I can scroll down to maximum, okay? And then it's going to ask you for your right bound and your left bound. And what that just means is if I'm looking for a point here, My right bound is somewhere over here, and my left bound is somewhere over here. And the closer you can get to the actual point there without going over, the faster it's going to calculate. Okay? And even if it doesn't calculate super quickly, okay? Even if it doesn't calculate quickly, it will eventually calculate. All right, so get somewhere close. So I would say if it asks for my right bound, I'd go right bound, left bound. It might ask you for a guess, so you just move it somewhere in there, and then you hit enter. And it will tell you, okay, x equals this at y equals this. All right, so you should be able to do that for those guys. And then finally here, sketching a graph of each function. I'm not going to go through that with you because I went through quite a number of examples the opposite way. All right, but again, this is all about finding your intercepts, okay? Finding your intercepts, knowing your end behavior, right? Knowing if it's going to go up or if it's going to go down. How many relative extrema can you have, right? And then getting a general shape of your graph, right? Getting a general trend there, okay? And again, make sure you at least try one or two of these, okay, and then see if your answers match up to the answers that are posted on Apex there. All right. A point 3 quiz. All right. So let's go through the checkup here real quickly.